As the last topic on optimization of vector calculations, we'll discuss a programming technique that allows you to express vectorization opportunities to the compiler in complex situations. This technique is called strip mining. We'll use it now to direct the compiler to vectorizable calculations, and also later in the course we will use this technique to rebalance parallelism between vectors and threads, and also as a basis for memory optimization techniques.
To illustrate strip mining, we will optimize an example application that performs binning of data. Specifically, we will use histogram construction to compute the distribution of the ages of a large people group. Our example is synthetic, but it represents a broad class of problems where binning is involved, including particle Monte Carlo, particle physics applications, and statistics. See this paper for an example application. In our problem, the input data is a long array called age. It contains ages of people from 0 to 100 years old as floating point numbers. The array is very large, in the hundreds of millions of elements, so it does not fit in the cache of the system. The output data is array hist, which contains the age distribution, in other words, the numbers of people in the age groups determined by the parameter group width. In our example, we have 5 age groups, each 20 years wide. So we want to compute the number of people between the ages of 0 and 20, and it will be the 0th element of hist. The number of people between ages 20 and 40 will be the first element of hist, and so on. We can make an initial approach to this problem by writing a single-threaded simple code shown here. In this code, we have one loop that iterates over all people. For each person, the loop queries the age, divides it by the group width, and rounds the result to an integer. The resulting integer is the index of the element in the histogram that is then incremented. This calculation obviously has a lot of computation, so can we use the performance of the vector units for it? If we can take one number, divide by the group width, and round it to an integer, we can also take a block of numbers, for example 8, load them into vector lanes, and apply division to the vector and then the rounding operation. Those are obviously SIMD instructions, single instruction multiple data elements. But at the very last step, when we need to increment the histogram bin using the index that we computed, SIMD cannot be applied. So in our example application, some operations are vectorizable, but others are not. And because of it, when we compile this application, the compiler will say that the loop cannot be vectorized due to vector dependence. This means that, unfortunately, all the operations will be performed as scalar math, even the operations where vectorization is, in principle, possible. To assist the compiler, we'll use a technique called strip mining. This technique transforms one loop into two nested loops. In the outer loop, the counter is incremented with a stride called the strip width. The inner loop iterates within that strip, as if mining it. We will see this technique used several times in this course. How does strip mining help us? Here we have a new code, which looks more complex, but essentially performs the same operations as the original binning code. Instead of one loop, we have nested loops. The outer loop iterates with a stride that we choose here as 16. The inner loop performs division by the group width, expressed as multiplication by the reciprocal, and conversion to an integer. The result is stored in a temporary container index that holds 16 indices. Then we have another loop where the indices are used to increment the corresponding bins in the histogram. Why is this implementation better? As you can see, we use strip mining and, in combination with it, split the loop into two loops, one computing only vector operations and the other computing only scalar operations. Thanks to strip mining, the length of those loops is only 16, so we need a temporary container for just 16 indices which may fit into the prod.surfs register file. Because vectorizable operations are no longer mixed with scalar operations in one loop, the compiler will be able to automatically vectorize the first loop and accelerate the multiplication and type conversion. The second loop will remain scalar, but there is nothing we can do about that, because the algorithm requires those non-vectorizable calculations. You can see that in addition to vectorization, we implemented here a scalar optimization technique called strength reduction. We replaced division by the group width with multiplication by 1 over the group width. Multiplications are much faster than divisions, so we can improve performance at the cost of slight change in the results. The performance results are shown in this plot. As usual, the green bars show the performance on the host system, and blue bars shows the performance on an Intel Xeon Phi coprocessor. Performance is measured in units of billions of values binned per second. Our code is single-threaded, so we should not expect that a Xeon Phi is going to be faster than a Xeon. However, the impact of strength reduction and vectorization with the help of street mining is obvious. Strength reduction improved performance by 60% on the host and by 160% on the coprocessor. After that, vectorization gave the host another factor of 2 boost, and on the Xeon Phi, performance improved almost by a factor of 3.
Of course, because the code is single-threaded, it is not using the multiple cores available both on the host and on the coprocessor. Later in the course, we will talk about optimization of multi-threading, and there we will revisit this example and see how thread parallelism will further improve the performance. If you have any questions, leave them in the comment section below this video. Thank you for tuning in, and I hope to see you in the next episode.